So I hope you can see this page right here. I took it from a book. This book is by Lubliner. I find this to be a better book than your textbook that I suggested earlier. So, I mean, in terms of the way the things have been described. So, you might also have a look at this book. So, can you see this page right here? If you zoom in a little, or directly from your screen, can you read what's written over here?
Yes, sir.
Yes, sir.
স্যার একটু জুম করলে একটু স্পষ্ট বোঝা যেত।
মুশকিল হচ্ছে জুম করলে আমি তাহলে লিখবো কোথায়? আচ্ছা ঠিক আছে, আমি দেখছি কি করা যায়। এবার ঠিক আছে? এবার পড়া যাচ্ছে?
হ্যাঁ স্যার, টেক্সটগুলো পড়া যাচ্ছে, কিন্তু এই যে এক্সপ্রেশনটা লেখা আছে ওইটা একটু বুঝতে অসুবিধা হচ্ছে।
ওকে ওকে, so what we can do is actually এবার বোঝা যাচ্ছে?
হ্যাঁ স্যার।
আচ্ছা, anyways, I'll write those things in the expressions that we are familiar with. So what they are saying, that there is a material that kind of obeys Mises plasticity. Which basically means when you write this expression, you see this earlier yield criteria was with respect to the stress. Now this time we are bringing in something called lambda, and we explain what lambda is and how lambda changes. Okay, lambda is always positive and always increasing. So it is basically the integration of the equivalent plastic strain. So this doesn't represent equivalent plastic strain, if you recall. So this is not equivalent plastic strain, because at any time equivalent plastic strain would be smaller than this quantity. Of course, we are talking about everything in relation to plastic strain. So there you have square root of J2. If you recall, this is essentially 1 by root 3 sigma equivalent in von Mises plasticity. And then you have your shear modulus as a function of lambda, right? And that actually has to be less than or equal to 0 every time. And when it is deforming elastically, then the inequality holds. And when it is deforming plastically, that's when the equality holds. Okay, so that's how you can interpret this first equation right here. Okay, and this Hij is Sij. It basically means you can represent the plastic strain increment. Okay, and this is not an equivalent quantity. This is the the tensorial quantity. Okay, so this can be written as d lambda times 3/2 sigma equivalent times S. Okay, now what they want you to show that also I'm trying to write in our expression. So d epsilon plastic is square root of 3 times S, the deviatoric stress, divided by 4 k squared k prime. Now k prime is your dk d lambda. Okay, and then you have then you have this other quantity which shows in something called Macaulay bracket. Okay, now what is the meaning of Macaulay bracket? This quantity equals 0 if x is less than 0, equals x otherwise. So if I were to represent a function y, which is Macaulay bracket, I mean x within Macaulay brackets, so this is what y is going to look like. Okay, so what they are writing within Macaulay brackets is this following quantity. You can go through that notation. That is actually indicial notation, and indicial notation in Einsteinian form. We have explained what is indicial notation in Einsteinian form. In Einsteinian form, you simply drop the summations. Okay, if let's say you are doing an inner product of S with its derivative. Okay, so that should be Sij dsij and summation over I and j. What Einstein proposed was that every time there is a summation, there is a repetition of index. And simply by showing the repetition of indices, you can represent the summation. So that's what they have done over there. Okay, so we'd like to prove this point number 1. Okay, so this is essentially S inner product ds. Okay, you might recall that J2 is essentially half of S inner product S. Okay, now while the material is deforming plastically, F has to be 0. F is always 0, which basically means if I take the differentiation of F, that also equals to 0. Okay, now if I try to take derivatives, okay, first I would take derivative of J2 with respect to sorry, like to take derivative of the square root of J2 with respect to J2, which would give me half J2 square root of J2 times d of J2. Okay, but then I can write d of J2 to be S inner product ds. Okay, and because there is s on either side, it's like, you are taking derivative of x squared. Okay, and that essentially becomes x squared is half x squared, so you take derivative, it becomes x times dx. Okay, it's similar to that. You understand what we are doing over here? So at first we took derivative of the first term with respect to J2, and then we took a derivative of J2 with respect to S. Okay, now if you look at this expression, it is like half of x squared. Okay, it is like half of x squared. Of course, it's not s squared, because square of s is a matrix. Okay, so hello, হ্যাঁ বলুন। না, আমি এখানে একটা ক্লাস নিচ্ছি, একটু যদি পরে ফোন করেন খুব ভালো হয়। হ্যাঁ, কি হয়েছে? আপনি আমাকে পরে ফোন করবেন, আমি এখানে একটা ক্লাসে আছি, ঠিক আছে? Okay, so S squared is a matrix. Okay, so it is a 3 by 3 matrix. But what we are doing over here is S inner product S, which is a scalar. Okay, this is equivalent to when you take two vectors and do a dot product. Okay, you see, when you take a dot product, you put a single dot, because essentially you are taking the inner product of a first order tensor. Since matrices are second order tensors, they have rows and columns, and vectors have only rows. So when you have rows and columns, so these are second order tensors, and when you take the inner product of the second order tensors, you put a couple of dots to represent them. Okay, so now if I take derivative, it essentially is going to be S inner product ds. And then the next thing that we can do is is k right here. So I can write it to be k prime times d lambda. Okay. Now, this expression, why do I need this expression? Because if you look at this expression right here, this doesn't have a d lambda. Okay, or this expression right here, this doesn't have a d lambda. Okay, so you need to substitute for d lambda, and this is what the expression of d lambda should be. So what did I do? I substituted for square root of J2, because this equality must always hold. Okay, because f should always be equal to 0 in plastic deformation. So there is no way square root of J2 is not k. So basically this can be written like this. Achha, one more mistake, it is k times k prime. Okay, so now you need to substitute this expression over here. Okay, and also substitute that sigma equivalent is your root 3 J2, which basically means root 3 of K. Okay. Now substitute the expressions for d lambda and sigma equivalent in this expression. Okay. Please remember, this is just a scalar. Okay, this inner product is just a scalar, so you can put it in the left, in the right, in the, anywhere, in the middle, everywhere. Just remember to put it in the numerator. Okay, so substitute for d lambda and sigma equivalent and check whether you get this expression right here. এই অবধি কি বোঝা গেল কি করছি?
হ্যাঁ স্যার। সাবস্টিটিউট করে কি এক্সপ্রেশন আসছে একটু বলবে? root 3 numerator root 3 into Sij into
তোমার কাছে এসআই তে কি করে এলো? আমি তো তোমাকে
S
এসআই দিয়ে কোনো এক্সপ্রেশন লিখিনি।
S matrix actually into S inner product ds আর ডিনোমিনেটরে 4k স্কয়ার k dash
k prime. Okay.
k prime.
But what is this fuss about having the Macaulay bracket? ব্যাপারটা হচ্ছে যে let's say you are deforming plastically and you are at this stress. Okay, now again I'm showing uniaxial stress. Okay, because that way we would be comfortable in understanding what's going on. Now, when if S inner product ds, okay, is less than 0, okay, which basically means you are not loading further, you are trying to unload from here, and as soon as you try to unload, okay, তার মানে কি যে আমার ধরে যাক এটা যদি আমার প্রিন্সিপাল স্ট্রেস স্পেস হয়, and তার পাশাপাশি যদি এটা hydrostatic axis, which basically is given by this following unit vector 1 by root 3, 1 by root 3, 1 by root 3, okay, transpose. So let's say this much is the hydrostatic stress, which would be sigma m root 3, okay. So this is the length of the vector. So when you take components along each direction, it is sigma m, sigma m, and sigma m. So that is the hydrostatic part of the stress. Then you have this deviatoric plane, and let's say this circle represents the current yield surface, okay. Of course there is isotropic hardening, that means as you develop more and more plastic strain, it increases continuously, it is increasing. So let's say right now, while having plastic deformation, you are at this point. So this is your deviatoric stress, okay. So hydrostatic stress plus deviatoric stress is your total stress. So what is your total stress? This quantity from the origin, okay. And if your ds, differential change in S, is either tangential or going inside, okay. So if it is tangential, of course, then it would be normal to your, because the deviatoric stress essentially represents the radius of the circle. So if you move tangentially, that is if you move along the yield surface, okay, that means if the size of the yield surface is not changing, okay, that would mean that d lambda should be 0, because k is continuously changing with lambda. I mean, k can have this following expression, like or something, okay. So k can have such expressions, so it is continuously changing with lambda. But if we're moving tangential, so this dot product, I mean, in principal planes, that would be essentially a dot product, and that dot product would be 0, okay. Whenever you try to move tangential, because your deviatoric stress is the radius, that dot product would be 0, okay. So so if you are moving on the yield surface, if you are moving along this yield surface right here, okay, without developing further plastic strain, so I mean plastic equivalent strain, I don't know whether how that would be even possible, because even if you are moving tangentially, you develop some plastic strain anyways. So possibly you cannot move tangentially. So in that case also, this is equals to 0. And let's say if you try to unload, that means if this is your yield surface and you are at certain deviatoric stress, okay. So, and let's say if I draw this tangent, okay. So if your ds ds, let's say this vector right here, okay, makes such acute angles with the direction of s, so this dot product would be greater than 0. It's not actually a dot product, it's a matrix inner product, but when it comes to principal directions, it is essentially a dot product. Okay, so this inner product would be greater than 0, but this becomes less than 0 when you go below this tangent and you start forming thetas that are no longer acute angles. Okay, and in such a situation, in such a situation, what would happen is you would be actually moving away from the surface, moving inside the surface, not just away, inside the surface. So basically, you would be unloading, and therefore your d lambda is actually either 0 or what I'm trying to say here is when this quantity is negative, that doesn't mean d lambda is negative. Okay, you are simply not getting any further plastic strain. So basically, when you are unloading, you are only deforming elastically. That we have discussed in extensive manner. So that's why here comes the Macaulay bracket, showing that the d lambda is so either though you are deforming plastically and this is true and d lambda equals this, for when you are not deforming plastically, okay, of course this would not be true. Of course this would not be true because f would not be equal to 0, but that case also can be incorporated in the expression of d lambda in the form that d lambda itself is 0 by doing this, by putting a Macaulay bracket. So at this point, this Macaulay bracket is just a fancy accessory just to say that when f is no longer equal to 0, when you are deforming elastically, okay, or when you are unloading, so your plastic strain would be 0, or the plastic strain increment would be 0, okay, and that unloading can be represented through s inner product ds being less than 0. Okay, so whenever this quantity is less than 0, you are unloading, and therefore your plastic strain would be increment would be 0. Okay, so that is just this Macaulay bracket is the fancier way to representing that. Okay, so are you clear with this part?
স্যার বলছিলাম যে এসটা তো একটা ডেভিয়েটরিকের সারফেসটা, তো এবার ডিএস মানে
Deviatoric
এস
surface is মানে
মানে
S is the stress. This is like the hydrostatic axis, and that axis is the axis of this cylinder, one Mises cylinder. And if you are on the axis, your equivalent stress should be 0. Sigma equivalent would be 0, or J2 would be 0, because J2 has this expression. So your deviatoric stress is also 0 when you are on this hydrostatic axis. Okay, and the von Mises criteria, which is, let's say, given by this, for a given value of k, let's say k is 100 MPa, for any given value of integrated equivalent plastic strain, that is not equivalent plastic strain, it is integrated equivalent plastic strain. So for any given value of this, okay, this basically makes, so what is s inner product s? That is like s1 squared plus s2 squared plus s3 squared in principal directions. So basically you are forming a circle. Okay, so basically it is saying the magnitude of s vector is a constant. Okay, when I'm representing in principal coordinates, s is a vector, so magnitude of that becomes a constant, okay, for any given value of k, which, if a magnitude is a constant, okay, essentially, and since the deviatoric stress can only change on deviatoric plane, so the deviatoric stress now is limited by this circle right here. Now you'll have to so whenever I I draw a deviatoric stress, that becomes the radius of this circle. এবার বলো।
হ্যাঁ, তো স্যার এবার যখন ডিএসটা যে স্মল এলিমেন্টটা নেব, তো সেটার ডিরেকশনটা তো ট্যানজেন্ট বরাবর হবে ওই সার্কুলার সারফেসটার।
হ্যাঁ, যদি যা
তো
খুশি
ওই
হতে
যে
পারে,
ভেতর দিকে
ঠিক আছে।
যেটা
না না
করছেন।
না, শোনো শোনো শোনো, এটা তো ডিপেন্ড করছে তুমি কত ফোর্স দিচ্ছ। হ্যাঁ, ধরো ধরো তোমার ডেভিটোরিক, মানে তুমি একটা বারকে ইলংগেট করছিলে, ঠিক আছে, ধরো এই কার্ভটা তুমি একটা বারকে ইলংগেট করছিলে, এবার তোমার মনে হলো যে এই লংজিটিউডিনাল স্ট্রেসের পাশাপাশি তুমি একটা ল্যাটারাল স্ট্রেসও দেবে, মানে তুমি একটা বেন্ডিংও দেবে, ঠিক আছে, বা তোমার মনে হলো যে তুমি অ্যাডিশনাল কিছু শিয়ারও দেবে। সো হতে পারে যে দিস deviatoric stress is changing in an arbitrary direction. The possibilities are the deviatoric stress could be changing along its direction, opposite to its direction, or anything in between. আমরা anything in between consider করছি, and that anything in between makes an arbitrary angle of theta. Okay, and if as long as that theta is an acute angle, then you are actually trying to expand this surface, and that is the nature of isotropic hardening. As k increases, the size of the k increases because lambda increases. You see, this is one of the most familiar expression for k. So k increases because lambda increases, and the size of the cylinder increases. Okay, but if this quantity makes an angle higher than 90 degree, okay, not an acute angle, probably called an obtuse angle, so then this inner product, in actual, when you are dealing in the principal plane, okay, so that inner product basically becomes a dot product, so that dot product becomes negative. But then you are actually, if you look at this diagram, you are trying to move inside the surface, you are actually kind of trying to unload. Okay, so that unloading would be, so this is like three-dimensional unloading. Okay, and that unloading essentially would be your elastic in nature, which basically means that's when f is no longer equal to 0. Okay, see, if you were to move outside, k also increases and adjusts itself, so that as j2 increases, k also increases and makes this f equal to 0. But if you try to reduce j2 by providing a ds which is in the negative direction, okay, because this dj2 is s inner product ds, and if this quantity is negative, then j2 is also reducing, okay, because dj2 would be negative. So if you are trying to reduce j2, okay, you see this k can never reduce with lambda, it can only increase, and because of that, this time you would be doing an unloading, and when you are unloading, you are not having plastic deformation, so f is no longer 0. Okay, f now becomes less than 0. Okay, and therefore this equation itself is not valid. This equation right here is not valid. This is only valid for plastic deformation. But if I want to club the elastic and the plastic deformation, okay, plastic deformation or elastic unloading, into a single expression, what I can instead do, because this s inner product ds is such a deciding factor, the very sign of itself can decide whether you are having plastic or elastic deformation. And when you are having elastic deformation, there is no plastic strain increment. I mean, there is plastic strain, that means the one that so far happened, like this one right here, okay, but there is no change in plastic strain. Okay, so d lambda is 0. So I can have a general expression comprising of both elastic and plastic type of deformation. Okay, so this Macaulay bracket gives you either 0 or a positive quantity. So it gives you gives you x when x is greater than 0, and it gives you 0 when x is less than 0. So when x is less than 0, or this whatever is inside Macaulay bracket is less than 0, your plastic deformation is 0, of course, because you know that in that situation you are doing an unloading, and you are only supposed to get elastic deformation in that case. And then if this quantity is greater than 0, okay, then this quantity would be would be representing the, the increase in the size of the yield surface. Okay, and therefore your d lambda would be this quantity right here. I mean the without the Macaulay bracket. Okay, that's when the equality holds for AF and also for DF. বোঝা গেল এই অবধি? আচ্ছা, তোমার প্রশ্নটা কি আমি অ্যাড্রেস করতে পেরেছি? Okay. Okay, let's move on to next question. And for that, we'll leave the central expression intact. We need that because this time they're asking to check the Drucker inequality. Okay. So they are telling you that show that the solid described in exercise 1 obeys Drucker inequality, which basically is d sigma inner product d epsilon is greater than equal 0. That is Drucker inequality. Okay, so that also we discussed in the previous week. So not only is sigma inner product d epsilon p greater than 0 because there is plastic dissipation, which is always positive. We proved that d sigma inner product d epsilon p is also greater than equal 0 when you have gradually hardening material. That means it's going like this and not like this. If it is gradually softening in some part, then that expression would not be true. Okay, so that's what I have been that's what you have been asked to prove also. So if it is gradually hardening, that means if k prime lambda is always greater than 0, okay, prove that. That is when this quantity is always greater than 0, and this should be simple. Okay, so what you do is you take inner product of this with d epsilon p, and that put everything which is a scalar in the left hand side, which is √3, then 4, then k squared, then k prime. Okay, and then this inner product in Macaulay bracket. Okay, everything inside, and then you have d sigma then S. Okay, now please understand that this one has a hydrostatic part, which is sigma m times I plus S, and this one we have shown a number of times that every time you take a dot product of a general tensor with a deviatoric tensor, okay, only that is equivalent to having the, sorry, this one is S, right? So okay, so d sigma d of this quantity, right? So this is equivalent to having S ds inner product S. And why so? Because let's say if I have a general symmetric tensor, not sigma m but sigma, and if I take inner product with a deviatoric tensor, okay, so I would be taking, so because inner product is a linear operation, I'm taking inner product with S, and then it is S inner product S, let's say. Okay, so if you look at the first inner product, that basically tells you that this quantity right here is a trace of S. Basically take all the diagonal terms of S and add them up. Now S being a deviatoric tensor, what is the value of trace of S?
0,
right? So as you can see, this quantity right here is also this quantity, and same thing applies to when you take the differentials. Okay, So this quantity being ds inner product s, which is exactly same as s inner product ds. You know, the nature of inner product. Inner product should be symmetric. Now, there are two situations. So case 1, S inner product TS, okay, is less than equal 0, which would mean that whatever is in this Macaulay bracket, that itself goes to 0, okay, which would mean this quantity is 0. So that is either plastic strain is not happening, or the plastic strain and the change in the plastic strain and the change in the stress, they are orthogonal to one another. That's what is meant by that. The second situation, where this quantity is greater than 0, which basically means this whatever is inside the Macaulay bracket, okay, you know, it's just the same quantity as this one, okay, because it is greater than 0. So then you have the following expression for d sigma d epsilon p, okay. Please understand that this is also an inner product. So this right here is a scalar. Now, would you agree this is the expression that we are getting? So one coming from the Macaulay bracket, because this time this quantity is positive. The other coming from this very expression right here. Okay. So in this expression, all quantities are positive except for k prime, for which we do not know the sign. But if this has to be greater than or equal to 0, okay, and since we considered that this quantity is actually greater than 0, which basically means none of the quantities are 0 and all are actually greater than 0, the only way this should be possible if k prime is actually greater than 0. But why are we considering two different cases? You see, this whole quantity should be true for every scenarios. So not only does it have to be true at case 1, it should also be true at case 2. Okay. So case 1 doesn't impose this condition right here. But when you go for case 2, that tells you that this is the only way you can achieve Drucker inequality. Okay. তো এই পার্টটা বোঝা গেল? কোনো অসুবিধা বুঝতে?
ঠিক আছে স্যার।
হ্যাঁ
স্যার কে টা তো কে ইজ এ ফাংশন অফ ল্যামডা।
ইয়েস,
হ্যাঁ, এবার ল্যামডা ইজ অলওয়েজ ইনক্রিজিং।
ল্যামডা ইজ অলওয়েজ ইনক্রিজিং।
হ্যাঁ, তো মানে কে ড্যাশটা পজিটিভ হতে পারে, নেগেটিভ হতে পারে।
Lambda is always increasing. I mean, look at this curve right here. So this is your sigma y0, the original yield stress, and at whatever stress you are now, that is your current yield stress, sigma y. Okay. Now the difference between the two is your isotropic hardening. Okay, I mean, this is actually your hardening stress. Actually, this is not k, it is actually √3 times k, because you know this k is in relation to shear stress, right? So k times √3. Now if you are following this gradually hardening curve, always k is greater than 0. Okay. And if you are following this curve right here, if the material is something like this, gradually softening, or it does have a phase where it is gradually softening, then can you see that this k prime is negative? Here it's a positive slope, but here it's a negative slope.
Yes.
Okay. So that situation is cannot be accommodated. That's the idea. এবার বোঝা গেল?
হ্যাঁ স্যার, ঠিক আছে।
Next thing, they are asking you to consider a stress sigma star, okay, which is inside of the yield surface. Okay, so let's say this is your yield surface, or if this makes you comfortable, a principal plane. This is your yield surface. Let's say this is where your stress state is sigma, and this one is your sigma star. Okay, show that S minus S star inner product is greater than 0. Okay, so what they basically say is J2, which is 1 by 2 is inner product is k squared, and J2 star, which is 1 by 2 is star inner product is star, is actually less than k squared, which basically means sigma star is inside of this yield surface. Okay, and now you'll have to first prove this. Okay, and this has nothing to do with isotropic hardening. This is a general matrix or general linear algebra. Okay, so if I take S times S minus S star and take inner product with S minus A star, okay, at least in principal plane, this means getting the magnitude. Okay, and actually, to be frank, in whatever coordinates do you take, or whether you represent the stresses as vectors like in principal plane, or as matrices, okay, this inner product is always greater than 0, because S and A star are not the same quantity. This is a non-zero vector whose magnitude squared are you trying to calculate. Okay, so this is always greater than 0. Now this can be expanded into S inner product S minus twice. Achha. So no. What I want to do is, so it can be written as S minus S star inner product S, then minus S minus S star inner product S star. So this basically means this quantity is greater than this quantity right here. Okay. Now this is true for all S star. Okay. Uh, with J2 star less than equal K squared. Now I got confused. So S inner is so S minus S star inner product S minus S star is S inner product S minus twice S inner product S star plus S star inner product S star. So that implies but how do we use this?
মাল্টি এক্সিয়াল ইনইকুয়ালিটি দিয়েও করা যেত না?
কি বলছো?
মানে মাল্টি এক্সিয়াল ইনইকুয়ালিটি যেটা আছে, যেরকম সিগমা মাইনাস সিগমা স্টার ইনার প্রোডাক্ট ডি এপসাইলন পিটা, তো ওইটা সিগমাটাকে যদি ভেঙে নিই হাইড্রোস্ট্যাটিক প্লাস ডেভিয়েটরিক পার্ট, আর ডি এপসাইলন পি ইজ
না 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 না
প্রপোর্শনাল
না
টু
না না
ডেভিয়েটিভ।
সেই পার্টটা তো আছে, সেই পার্টটা তো আছে। ওকে, বাট এখানে এইটাকে আগে প্রুভ করতে হবে that this quantity is greater than 0. তো এই পার্টটার প্রুফটা এই মুহূর্তে আইডিয়া করতে পারছি না। So let's move on with the second part. Okay, which says that show that this quantity sigma minus sigma star d epsilon p is greater than equal 0. Okay, so this is the maximum dissipation postulate. Okay, we discussed about this, that this causes for maximum dissipation. So basically, of all the stress values that the material could have attained, it attains the value which corresponds to the maximum dissipation. That's what this means. So let us try to prove this. So if I take so assume this quantity is true and try to prove this. So if I take inner product like this, so as we discussed earlier, only the deviatoric components would matter, because every time you have, because you see the plastic strain is proportional to deviatoric stress. So every time you have an isotropic stress component, that simply would give you an inner product of trace of that deviatoric quantity. So which is basically 0. So essentially you can take out the hydrostatic part. So this is true, this equals this. Okay, now if I write the expression for d epsilon p, so I have this square root of 3 4 k squared k prime. Then what expression do you have? This quantity right here, s inner product ds. Then s minus s star inner product কি এক্সপ্রেশন হবে? ডি এপসিলন পি এর এক্সপ্রেশনটা একটু বলো। আমার কথা শোনা যাচ্ছে?
হ্যাঁ স্যার, √3
তারপর
ইন্টু এস ইন্টু ব্র্যাকেটে এস ইনার প্রোডাক্ট ডিএস
within Macaulay brackets, right?
Macaulay brackets, yes, divided by 4 k square into k prime.
Okay, so look at this expression. So again go back to this expression right here, df, which says 1 by 2 root J2 times S inner product ds. Okay, so that equals minus k prime times d lambda. D lambda, of course, is greater than 0. Now there are two ways this is possible. One is k prime greater than 0. Okay, in that case, S inner product ds would be greater than 0, which would mean this quantity would be same as S inner product ds, and since this quantity is also greater than 0 and this quantity is greater than 0 and k prime is greater than 0, then this whole quantity, then this is what we are trying to prove, then this whole quantity is greater than 0. Okay, but if k prime is less than 0, that would mean that S inner product ds is less than 0, which would mean S inner product ds within Macaulay brackets is 0. Okay, so this quantity right here, inner product d epsilon p, would be 0. So in two situations, okay, together what we have is greater than or equal to 0. So we are considering two situations. In one where k prime is greater than 0, and in the other where k prime is less than 0. Okay, we have already, this is what is to be taken from here, that we can assume this quantity to be already greater than 0. আচ্ছা, এই পার্টটা কি বোঝা গেল? সেকেন্ড পার্টটা, দ্যাট দিস কোয়ান্টিটি উড বি গ্রেটার দ্যান অর ইকুয়াল টু 0.
স্যার ওইটা তো আগেই করেছিলাম।
না না না,
এই সিগমা মাইনাস সিগমা স্টারটা করিনি আগে, ইনটু ডি এপসাইলন পি ইজ গ্রেটার দ্যান 0।
বোঝার চেষ্টা করো। So this we did to show if the maximum plastic dissipation postulate were true, that can be represented like this. Okay, and if the maximum dissipation postulate is true, then the yield surface is convex. Okay, now we are taking a particular example, and in that example we are trying to show that with a certain yield surface, that is von Mises yield surface, and certain type of hardening that we have taken, okay, it obeys the maximum dissipation postulate. Here actually you are trying to prove that this quantity is greater than equal to 0, given this expression right here. Okay, বুঝতে পারছো কি আমার কথাগুলো?
হ্যাঁ স্যার, বুঝতে
আর
পেরেছি।
একটা অদ্ভুত ব্যাপার, তোমাদের না বুঝতে পারলেও কিছুতে বলবে না যেটা বুঝতে পারছি না বা কিছু, চুপ করে সবাই বসে আছে। Anyways, let's say for the first part where you know we are talking about this inner product right here. Okay, now let's look at this. Let's say these are the principal directions. And let's say this is the von Mises yield surface in the principal, in the deviatoric plane. Let's say this is the center. So let's say this is the hydrostatic axis. Okay, and let's say this is a stress as in measured from the origin. Okay. But we would be taking the deviatoric stress, which is the S. Okay, and some other stress state which is inside the yield surface. So this is the sigma prime, sigma star. Okay, and therefore from the center of the von Mises circle, this is S star, and therefore this quantity right here is S minus S star. Okay, now this can be an indirect proof to what we are discussing. So this center right here, this all this S vectors, these are all on the same plane, deviatoric plane. Okay. Now this A star could be anywhere within the circle. Okay, if it is inside the circle, okay, there is no way this S minus S star inner product S, okay, is greater than less than 0. Okay, I mean, let's say if I extend the direction of S like this, and if I have to have a vector which makes an angle, okay, so let's say this angle is theta, this angle right here is theta, which is less than 90 degrees. Okay, and if I have to have an angle which is greater than 90 degree, that would mean if this is the tangent, let's say, it would have to first align with itself. This S minus S star must be at an angle greater than 90 degree. Now this tangent is at a 90 degree angle, so in order to have an angle greater than 90 degree, the S star that we are talking about must exist outside of the cylinder, and if it is inside the cylinder, so this angle is never greater than 90 degree. So this inner product right here is greater than or equal to 0. Okay, so you see this angle, in order to have this angle theta to be an obtuse angle, this A star must exist outside of the yield surface. Okay, it cannot even be tangential, it cannot even be anywhere on the yield surface. If it is inside the yield surface, the angle is always less than 90 degree. You can take anywhere. Okay, it is always less than 90 degree, and therefore it is always going to be the inner product is always going to be greater than 0. Now here we are talking about taking an inner product in the principal directions. But can I show that this inner product, whether you take in the global Cartesian or in the principal directions, you still get the same values? To do that, let's do this. If I, let's say, have two matrices A and B, and if I take the inner product of the two, this can be also written as the trace of B transpose A, or trace of A transpose B. How so? A inner product B is a summation over I, summation over J, A I J, B I J, which could also be written as summation over I, summation over J, A I J, B transpose J I. Now, if I do a summation over J, that is summation over I, A times B transpose I, which is a trace of AB transpose. Okay, and it can be very easily shown that that is also trace of B transpose A. And actually, I could, instead of taking B transpose, I could have taken A transpose. So this can be written as a lot of things like this. B transpose A is already written. So B A transpose or equal to trace of uh, AB transpose, and so on. A lot of things can be written. Now, if I take, instead of A, if I rotate A into a different coordinate system, okay, which could be also the principal directions for the stress matrix, and take inner product with B, that would be trace of A, trace of this times this transpose, right? So Q A Q transpose, and then transpose of this, so Q B transpose Q transpose, and this is how transpose works. So you take the the matrix in the most right hand side, take the transpose of this and put it in the extreme left. So Q transpose transpose is Q, then B transpose, then Q transpose. Now this Q transpose makes an identity matrix. So Q is a proper rotation, which is same as plus orthogonal tensor with positive determinant, which could also be written as trace of, as you can see, uh, as we discussed, trace of AB is also trace of BA. So what we can do is we can write it to be Q times A B transpose Q transpose. So this is like my new A and this is like my new B. So I can write it to be A B transpose Q. And again, this makes an identity matrix. So this equals to trace of A B transpose, and therefore this also gives you A inner product B. So the inner product doesn't change if you change the coordinate system. So instead of taking the global Cartesian, if I were to represent the stress in the principal directions, okay, the inner product would not be changing. Okay, so So this inner product right here, okay, is I mean, I can, take the example of the principal directions and show that this quantity is greater than zero, okay, irrespective of the choice of your coordinate system. So that proves the first part of the expression, and with the help of that, you can prove the second part. Okay. So let's move on to the next question. Uh, let's skip this one. Okay. Let's move on to question number 5. So this tells you that for the same material, show that this could be the expression for the plastic strain increment. Now, please note these two strain increments. So this is the plastic strain, and this is the total strain. Okay. Now, the total strain increment, okay, can be written as the following: the elastic strain increment, and then the plastic strain increment. Okay, and the elastic strain increment is in two parts. There is a volumetric part, which would be like kappa times trace of okay, sorry, no. So your hydrostatic part of the stress divided by kappa, actually divide that with 3, and then multiply with an identity matrix. So actually what we can write this to be like so there is the volumetric part of the strain, and then there is the strain deviator in the elastic part. Now this quantity right here can be written as twice mu, 1 by twice mu times ds, and then you have the plastic strain, which can be written as 3 by 2 sigma equivalent um, d lambda times s. Okay, so this mu right here is same as the shear modulus. So I hope you understand where it is coming from. So stress is like lambda times trace of epsilon times I plus twice mu epsilon. Okay, or I mean this is all elastic part, or this could also be written as lambda plus twice mu by 3 times trace of epsilon times I plus twice mu epsilon d. Epsilon d is a strain deviator, which is essentially your epsilon minus trace of epsilon divided by 3 times the identity matrix. Okay. So this is like the equivalent of deviatoric stress. So this could also be written as the hydrostatic part of the stress plus the deviatoric part of the stress. Okay, so you can see this AS is actually proportional to epsilon d, because this is what is corresponding to the hydrostatic part, and this is what is corresponding to the deviatoric part. Okay, so this basically means ds equals twice mu d epsilon d, and that's where this is coming from. And this is like the volumetric part of the strain. This is actually the volumetric strain, and this right here is your bulk modulus. Okay, so now if I write this expression for the total strain increment, okay, from that I can write S inner product d epsilon is 1 by twice g, because you see the inner product with the volumetric part will require, the trace of S, and that would actually be 0, but then this part would be S inner product ds, then 3 by 2 d lambda sigma equivalent S inner product S. Now this 3 by 2 S inner product S is basically this two quantities is like sigma equivalent squared, and when you divide, then you have this expression d lambda times sigma equivalent. So sigma equivalent, as we discussed, square root of GA2 times root 3. Okay, and from the yield criteria, J2 minus k equals 0, we have J2 equals k. Sigma equivalent is k times root 3, as we discussed earlier, and And then we have this giving us that d lambda equals S inner product ds 1 by 2 k prime, right? Okay, so substitute this expression over here and substitute the expression for sigma equivalent. Okay, and then try to represent S inner product d epsilon as S inner product ds. So you'd get 1 by 2g plus from over here root 3k divided by twice k prime, right? And then substitute this expression to this expression right here, which is d epsilon p equals root 3 s root 3 times s inner product ds 4 k squared k prime. So in that, substitute the expression for S inner product ds. And check whether you get the same expression. I mean the desired expression. Is it like d lambda was possibly k prime times k, right? Because dj2 should be square root of j2 minus k equals 0. So df should be 1 by twice k, because that is j2 square root of j2. Then dj2, which is s inner product ds minus k prime times d lambda. Okay. So d lambda is k prime. So which basically means I need to bring in k over here. So this simply cancels out. এই পার্টটা কি করছো তোমরা?
হ্যাঁ স্যার করছি।
এখানে যে ডেরিভেশন গুলো করা হচ্ছে সেগুলো একটু বাড়িতে নিজেরা প্র্যাকটিস করো। হয়তো কোথাও কোথাও গ্যাপ থেকে যাচ্ছে, সেটা বুঝতে পারো।
হ্যাঁ স্যার আসছে।
ওকে, ঠিক আছে। আজকে যে অঙ্কগুলো করলাম, এই লেকচার ভিডিওটা আবার দেখো, দেখে আরেকবার প্র্যাকটিস করো। ঠিক আছে, আমার মনে হয় কিছু কিছু গ্যাপ তোমরা বুঝতে পারবে যে কোথাও কোথাও বোঝার তোমাদের অসুবিধা আছে নিজেদেরই। এবং হয়তো পুরনো কিছু লেকচার্সও দেখতে হতে পারে, সেগুলো দেখে ইউনো নিজেদের আজ অব্দি যতটা পড়ানো হলো সেই অবধি নিজেদের প্রিপেয়ার্ড রাখো। So today we don't have enough time, but the plan was to start with